So let's learn about the electric displacement vector. Let's say this is this capacitor is a dielectric which has taken approximately all the space. It's connected to the positive. Let's connect it to the negative. It has a positive Q charge. It has a negative Q charge. And so the negative charge of the dielectric gets accumulated. Now the let's learn about the polarization. What like the polarization vector? What is polarization? So polarization is defined as a dipole moment. Here the dipole. Let's say the length is L. Is defined as dipole moment per unit volume. Dipole moment per unit volume. Let's say the cross-sectional area of this dielectric is A. The electric field, uh, how would that be? Electric field due to this polarization, just this electric field called due to the dielectric, in the vectors form is defined as negative of the polarization vector divided by epsilon. Why negative? Why? Let's learn about this. See, if you have a dipole moment is from negative to positive. Well, the electric field is from positive to negative. So the electric field is negative of the dipole. Alright. And the y upon epsilon naught. This. So we know the dipole moment. Uh, See the field due to polarization. Let me give you the units. See, dipole is basically charge into the length. This is the length L is charge into the length L. When we divide by the volume, let's say the volume is L into A, then we get the charge density. The Q by A is the charge density, also defined as sigma. So you can say the dipole moment per unit volume or the polarization has the same unit, has the same units, has the same magnitude, same value as sigma, the charge battery. Dipole moment, how much that is? If there's a charge Q, if there's a charge, let's say a QP minus QP, and there's a plus QP charge here. The dipole moment is of course QP times the length L, and per unit volume is length into length divided by area. That is sigma. And it is generally, I have reduced it for a rectangular slab, but it is true for any surface in general. Okay, so because it's basically two, we can say there are two plates of charge. Better choose a word. There are two plates of charges, like few atoms thick plates of charge. We can use sigma by 2 epsilon to calculate the electric field due to them. If I consider a point here, then the electric field due to this will be in this position and this positive charge will be here. If I consider it as a positive charge, so they will get added. And then sigma by 2 epsilon gets sigma by epsilon naught, makes sigma. And we know sigma's value is the same as the polarization with the dipole moment per unit volume. So it's P upon sigma by epsilon naught or P upon E. And then vector sum, of course, is minus P upon E because the distance is opposite. Now, the net electric field due to this dipole and no, sorry, this dielectric and the capacitor, net electric field will be, let's assume E naught is a field due to the conductors and this EP, which is minus P. Let's use vector there upon epsilon. Can take it to the other side. We take it to the other side. And now we can integrate both sides. Have a dot product with the area vector. You can do this, it's mathematically feasible. Now, what if you take, let's say, take the epsilon naught, take the epsilon naught here, then you integrate. Of course, there will be an epsilon naught here. How much is this value? How much is this? So let's assume the dielectric wasn't there. There were just two plates. There's two plates. They have an electric field of E naught. They have the same charges plus Q and minus Q, right? Electric field E naught. Now, by the Gauss's law, if we take this as a Gaussian surface, we have to go to the electric field here. Gauss's law, this electric field that is E naught to ds, which is actually pi r square, is equal to charge, this charge, let me call it the charge inside, it's called the free charge actually. So QF by epsilon naught. Let's not take pi r square. So let's not take pi r square. Because in the charge will be some limited to some circle. Uh, mm, mm, wait a second. So let me consider not this as the Gaussian surface, but this as the Gaussian surface. This whole cylinder. Then the charge inside is of course QF. And let me not calculate the area. It's E dot ds. We know it's QF by E. Or in other words, in E0 or E naught, epsilon naught dot ds is QF. It's an equation. You can use the same equation here. E naught epsilon naught ds is QF, free charge. You can write it as QF, and this whole quantity is the electric field displacement vector. So the electric field displacement vector is defined as epsilon naught E plus P. In other words, like if you know that there is no dielectric, this polarization becomes zero, and the displacement vector is just epsilon naught E. And in case of homogeneous dielectrics, isotropic dielectrics I'm talking about, then what happens? Okay, one thing was, wait a second. I took this to the other side. It's E vector plus P vector upon epsilon naught is equal to E naught. I take E common, epsilon naught common, sorry. It's not epsilon, it's E vector. E naught vector. I'm getting confused. It's E naught vector, epsilon naught, and you have E epsilon naught here. And this is described as D vector. And this is also, of course, D vector, right? In case of homogeneous dielectrics, we have the formula. The net electric field is the electric field to the conductor divided by K. It's E naught. So we can write it as EK, right? It's D. And this can be written, also can be written as KE vector epsilon naught is equal to D. Well, if we put it in the formula that we derived just above, but which formula did we derive? We derived D vector. The ds, it was the charge free, right? It's charge free d dot ds. If we put it in this form, we put the value of d, then we get integral of k e vector epsilon naught dot ds is equal to the charge free. If we take the epsilon naught here, then we get another form of the Gauss's law. Another form of the Gauss's law. If we let's the integral should be the surface integral. Because we're talking about the ds which is on surface, so let me write it as the surface integral everywhere. We get another form of the Gauss's law. And it can be derived in some other way too. What way can we derive it? Well, let me. So if like consider a Gaussian surface, we consider this cylinder as the Gaussian surface, then it has both the charges, the free charge and the bound charge. I think the free charge is called the bound charge. Not sure. Mhm. No. It's called the induced charge, and this is the free charge or the bound charge. Oh, the induced charge is also called the bound charge, and the charge on the conductor is the free charge. But the Gaussian surface because it has both the charges. So if we consider the electric field, the ds, that is the charge inside, which is the charge by the free charge and subtracted by the induced charge upon epsilon naught. And we know the formula for the induced charge is q1 minus 1 by k. We can simplify this. Uh, Minus k and plus k by q. So it gets subtracted and the k gets on the other side. So the charge free times k dot ds. Charge free comes out. I can drive it another way too. And why do we have another thing? Why do we have qp is equal to q1 minus 1 by k. To know the derivation, let me derive that because we are, deriving a lot of things. So let's go with the flow. So how to derive this? See, the electric field due to this dielectric is q a epsilon naught, and due to this conductor, the capacitor, not the capacitor. When you're talking about the capacitor, you talk as a whole. Talking about the conductor, it's q upon qf upon a epsilon naught, and of course, opposite sign is the net electric field, right? But the net electric field, by definition of the dielectric constant, is defined as E over epsilon naught. How much is this E? E naught, sorry. E naught is the QF upon A epsilon naught divided by K. That's the definition of the dielectric constant. And of course, you multiply the whole thing by this K and take it out. And so KQF minus QF is equal to KQP. QP is equal to, take QF common, K minus 1, divide by K, which after simplification becomes 1 minus 1 by K. That's how derived is. So yeah, that was the derivation. Basically, an alternate form of Gauss's law and the the electric displacement vector. Okay, bye.